Thanks everyone for coming tonight. This is a great surprise for the H2O team because we've been on this journey for a long time, but this is one of the first meetups that I've ever been invited to that I haven't planned or had to work on the food and everything. So we're super excited about learning more about the use case. So they just asked me to maybe introduce the company and the product. As he mentioned, I'm Josephine Long. I'm the head of customer experience at H2O. So maybe you could just sorry. Can you maybe make it into? Yeah, thanks. So H2O.ai, if you haven't heard of us, we're a startup out of Mountain View, California. We were founded in 2011. We debuted our product H2O in 2012. H2O is an open source in-memory prediction engine for machine learning analytics. We've taken some, sorry. Great. So we're a team of about 55 people, which we've grown tremendously over the last 2 years since I've joined the firm. It's a glimpse of our executive team. Shri Satish Ambati is our CEO and co-founder. Shri was the VP of engineering at DataStax and worked on the original Cassandra project and at different Silicon Valley firms. Cliff Click is our CTO and co-founder, and Cliff actually was on the team at Sun Microsystems that invented the Java Virtual Machine hotspot. So we're a team of distributed systems engineers that have created this scalable, performant machine learning platform. And we work with our academic advisors out of Stanford, folks like on this slide, Trevor Hasty, Stephen Boyd, Raf Petrani, and they've helped us take some of the algorithms that they've created and make them fully parallel, distributed, and run in memory across distributed systems. And it's really exciting because they're literally in our offices on a monthly basis. They send us their best PhD candidates with cutting edge new algo techniques, and we get to incorporate that directly into the product. So what is H2O? It's an open source in-memory prediction engine for machine learning. We've taken some advanced algorithms like deep learning, gradient boosting machine, random forest, and we've made them fully parallel, distributed, and run in memory on top of commodity hardware, on top of Hadoop, and on top of Spark. We've also written some full-blown APIs, so you can use the front-end interfaces that you're familiar with. Things like R and Python, so we scale R and Python. You don't run into some of those limitations you might if you use it on the desktop. And since the entire platform is written end-to-end in Java, so one of our main value propositions is once you build a model and store it, you have the ability to export the plain old Java object or the POJO to go directly into production. So a lot of our customers are now able to enable real-time analytics throughout the organization and get productionalized models a lot faster. The model object is written in a Java code where it's optimized Java code. We JIT the code and it can run in your L1, L2 cache line, so it runs in nanoseconds potentially, depending on the architecture. This is a list of the supervised learning algorithms in H2O. We have general linear models, naive Bayes, distributed random forest, gradient boosting machine, and deep learning. And then from an unsupervised perspective, we have k-means, principal component analysis, generalized low-rank models, which is a new technique that actually just came out of Stanford, and autoencoders. So from a high-level view, kind of a architecture slide starting on the left, we can ingest HDFS, S3, SQL, and NoSQL data sources. You have automatic in-memory columnar compression, so depending upon the shape of your data, you get an automatic 3 to 5 times compression when you parse it into memory. H2O itself is our own version of in-memory MapReduce, which allows you to do distributed calculations on the cluster. So we're not really leveraging Hadoop's MapReduce, we're leveraging our own version of in-memory MapReduce. We're kind of using HDFS from a Hadoop perspective. And then you can do some basic feature engineering, some munging techniques. We're adding a lot of munging capabilities in one of the next generations of the product, and then run some of the algorithms that I mentioned before. On the top are the different ways you can interact with the product. So you can use R, Python, as I mentioned. H2O Flow is our own graphical user interface that you could use, as well as JSON, Scala, Java, and we have hooks into Tableau and Excel. So it's been a great experience with H2O over the last couple of years. We've been able to sign up lots of enterprise customers doing cutting edge things with machine learning. November of last year, we had our second annual H2O World event in Mountain View, California, and we had about 700 participants and maybe 30 customers speak on what they're doing in reference to H2O and machine learning. It was a great conference, and I think some of the people here attended the event. And all of that content's available online. So I think the last thing I'll say is that we really believe in the machine learning community. We're looking to bring, algorithms, machine learning techniques to the masses and enable people like you to do things you could never do before with this type of technology, enabling all of your data and kind of solving the next generation problems. So thank you for your time tonight, and I look forward to the presentation.
Thank you very much, Josephine, and thank you very much she actually brought a few books on deep learning. If you haven't taken the book, actually go ahead and take it when you are on the way out, or if you want, I can pass it around as well. We also have some stickers of H2O. Should I can do that? Just pass it around if anybody wants to read that. We also have some stickers here if you would like to take it out and put it as a swag on your laptop. Show some love. Little shameless plug, Colaberry is the organization where I came from and some of the organization team came from. Can everybody from Colaberry just wave your hand, stand up please somewhere. Thank you very much for everybody from behind the scenes making this event happen today. We do lots of consulting work, product development on data science specifically, but we also help people to move into data science. So that's why we call ourselves a School of Data Analytics. And it's a funny way, actually, if you look at our Twitter handle is Colaberry Soda. It stands for Colaberry School of Data Analytics. So if you would like anything, or if you want to tweet about it, use the Twitter handle Colaberry Soda. And before we start, I would like to ask, how many of you already know about H2O, or at least heard about H2O? Can I have a show of sign? Thank you. And how many of you are already using it, not at deployment level, but just trying it out right now? A few of you. How many of you have already deployed it into production? Thank you very much. So we have, as a community, we also all want to learn from each other and build on each other and make the data science community a much better community day and day on. And as you already know, it is the sexiest job of the 21st century, but we will make it happen. Everybody is good with that? So let us make it happen. I would like to bring on Josh onto the dais and then start his presentation, and he will introduce himself in the data science way. Thank you, Josh.
So Merle's mentioning sexiness and all this kind of stuff, and then they bring me up here, and quickly that diminishes pretty rapidly. So. Well, first of all, thank you, and we are excited, humbled, and honored all at the same time. So thank you for allowing us to come up here and listening to me ramble on about data science and hopefully healthcare and the way to be able to distribute this over programming language in R. Josh. Hello. This is working.
It's fine. Speak a little bit louder. Texas guy.
Yeah. No.
Yeah.
Huh? All right.
We can hear you pretty good.
Okay, here we go. I'll try to speak as loud as I can and chug some water as I go. Like Merle said, my name is Josh Smitherman. I'm Chief Data Scientist for Colaberry. I've been in multi-level projects around retail and in manufacturing and in healthcare. I've worked with healthcare providers in the UK and also within the US and in the government. Most of the experience here with some major companies here, so I don't really like talking about myself, but there I am. what we're going to be reviewing today, and what I wanted to share with you guys, is reviewing a technical paper. So this is obviously not written for a technical crowd, but many of you have some technical background. We'll point you to the technical paper, so everything we discussed today you can download and try yourselves, because obviously you like to play like as data scientists, you like to get your hands dirty in it, and you want to be able to see how it works. So there's a technical paper that allows you to reproduce everything that we talked about today. We're going to quickly review Colaberry Data Science Center of Excellence, and the key features that we're going to be looking at today is H2O and R, how does it work together to really solve a problem such as in the case of diabetes. And we'll be talking about exactly what that means from some of the data sources that are available here and how we can go about solving that. But real quickly, I always have to throw this disclaimer. I'm not a PhD physician in medical practices, so every bit of information here does not mean you can self-diagnose yourself with diabetes or take any sort of actions. Obviously, see your primary care physician or certified medical professional to be able to get that information. So there you go. There's your disclaimer. So, a little bit of icebreaker here. So, dealing with healthcare, in the Rogaine area, this might happen to you if you're a data scientist. My doctor says my hair loss is caused by worrying about data loss. So, if you ever worry about this? This was my favorite. So, I don't like the look of this. Searching for gravy and turkey. Stephanie was going through the roof during Thanksgiving. And then this is my favorite. This is all about the data science being sexy. If this is not sexy, I don't know what is. But in reality, so what we're going to be talking about today is like I said, there's a technical paper that was written in the Data Science Center of Excellence. Technical paper will review everything that we're talking about here that you are able to reproduce, and includes all the R code. But a quick preview into what the R code or the technical document is going to include. Includes the k-means clustering, the H2O AI deep learning and gradient boosted machine, and the general linear model and the distributed random forest methodology of categorizing diabetes and predicting that through a binary case, and binomial distribution, obviously. And in the Data Center of Excellence, you can look at more of our services and how we deploy those capabilities. So I'm going to kind of breeze through this a little bit because I'm assuming that most of you have heard of R, you understand what R is, so I kind of get that. But just for those that don't, just kind of, if you already do, then just kind of bear with us. But R is a cutting-edge machine learning predictive analytics statistical tooling that you can integrate in with different IDEs such as RStudio. It allows you to run statistical models on data sets of various sizes. It has a large community. In fact, one of the professors I work with at the university back in Dallas, Texas, Southern Methodist University, together I was able to work on a project. He wrote the A-rules package in R, which is the affinity rule mining for market basket analysis and sequencing analysis for that piece there. So a lot of community universities and professors and institutions, and also from the commercial aspect, contribute to this growing levels of package contributions. And best of all, it's free. Who doesn't like free? Now, as you heard before, H2O AI is a open source package. And what I love about H2O is being an R and Python guy, and also, obviously you started out in SAS, but, looking at some of these open source technologies and how does H2O really help us, parallelize a lot of our computationally intense code and be able to do some of these machine learning algorithms in a very fast and easy way to be able to run these both on the application side and on the research side. So if you're prototyping, coming up with a proof of concept, you're doing a quick and dirty, but it's a huge amount of data, H2O is a great tool. If you're wanting to move that into an application, H2O is a great tool that you can leverage that. So it has many of the packages that you are familiar with in R. It also includes several great features within the deep learning algorithms, which has various aspects of neural networks that are really great, and also the deep learning algorithms and distributed random forest and gradient boosted machine learning. I quickly became a fan once I started using those. So how does it work? So if you're not familiar with H2O, it's just basically a wrapper around some of your APIs. If you're in your R Studio session or if you're in your IPython session, you just basically, initiate your instance of H2O. It, clusters and optimizes the PC, and you send the code in there, and it crunches it and submits back your results of your models super quick. So that's the technical side. Let's talk about the business application side. So in healthcare today, there's a growing need for pay for performance, not and pay for outcomes instead of paying for procedures. That's a big mantra in healthcare right now. So there's many institutions and healthcare institutions that are looking for ways to help justify the cost of healthcare. And one of those ways is identifying risk of certain potential categories of chronic diseases and looking at the treatment options and grouping those together to say, is this treatment option good fit for you, and what are the risks or reductions of risk? Is that worth it to you? So if we have to put you on this expensive medicine, or you have to go through this expensive treatment option, you would like to know what percent reduction of this, either if you do not have the chronic disease, reduction of the likelihood of getting the chronic disease. If you have a chronic disease, what's called the value of life here metric, which is really developed by the Archimedes model, which is a model that's used for differentiating equations, basically projecting your life's quality if you are dealing with a chronic disease versus those that do not. So it's a neat measure there. So the CDC, which is Centers for Disease Control, publishes the famous NHANES data set, which is a data set that contributes to surveyed around the nation of many different hubs within the United States. It features gender, age, race, education, marital status, whether you smoke, how much drugs have you used, and sexual partners, blood pressure, alcohol usage, a myriad of different social and economic and health statistics. We're going to use these through H2O and R to predict and categorize diabetes cases within each of these makeups of these profiles of these cases. So what our goal here is to analyze these variables and features and to flush out and group of these. What are the key contributing features that contribute most highly to the binary predictor of whether you will get diabetes or not? Does that make sense? So a quick EDA, exploratory data analysis. We want to look at our NHANES data and say, okay, so what does this make up? What are we dealing with here? So right here we're dealing with a population of about 14% currently diagnosed with diabetes. Typically the worldwide statistic is 8.5%. So clearly we're dealing with what's called a class imbalance problem. So we'll talk more about that later in a lot. What H2O contributes in that particular fashion and how we treat imbalance problems when we're doing prediction. Gender population, proportion of diabetes, almost the same between male and females. When we look at education and performance, and this is really small, I apologize, but this is eighth grade education. Seems to be the highest proportion of receiving diabetes. Followed by, I believe that's ninth, I can't really read it right there, that's college education, high school, some college. And then here we have the race here, and this is white, other, Hispanic, or Mexican, Hispanic, and Black. So again, you can see those proportions there of the diabetes cases there. So now that we've kind of reviewed the NHANES data, we kind of got our business case. We want to predict diabetes. We have R, we have H2O. So what are we going to do? The first problem we're going to run into when we deal with a data set like this is the problem of missing values. It's loaded with it. So in many of the cases that you probably have seen, and this wreaks havoc on your analytical projects, you have to have what I call an NA strategy. What are you going to do about it? Well, you could delete the values. You could, you could ignore those values. You could delete the row. If we were to do that here, we would have no rows. You could, so what's your strategy then? Since this is survey data, and I'll give you an example. In healthcare and the survey aspects, people are probably less inclined to answer to certain questions they don't want to answer, for obvious reasons. But they may answer more highly to other questions, such as, pregnant women may not want to divulge the information that they've smoked. That makes sense. Or if you are a certain, or given another information. What the data imputation function within H2O can allow us to do is profile each row and column and allow us to loop through the computational distribution system that it's going to localize, optimize on our system. We can profile and guess based off certain central tendency, mean, median, mode, and profile that specific case and say, yep, that looks like a smoker, and it's going to impute the value. Does that make sense? So we have 32 cases out of 78, 41% we have NAs. Now, at some degree, data imputation is a fascinating field of study, and it gets quite complex. If you've ever used the mice function, which is multivariate imputation function for imputing values, it gets highly complex, and it's you want to kind of take this with a grain of salt. The H2O functions within this is a simple imputation. Obviously, it can be expanded, but the mice package within R as well kind of gives you, if you haven't checked it out, check that out. Read about the mice package, M-I-C-E, and it will kind of give you an idea the problem of data imputation and the complexities around that. But the good thing is that there's solutions here. But we are going to make the assumption that, and this is no hard and fast rule, anything 75% or less is just, we're not going to be able to impute enough values or get enough of samples to be able to impute logically without disrupting the overall distribution and structure of the data. That's the biggest thing when you do imputation. So data imputation, we're going to take these missing values, we're going to feed it through R and H2O, it's going to impute the values, it's going to use other columns and values to be able to impute this, and then it's going to give us our value. Now if you're just doing this locally, and I've done this many of times using mice, it takes a long time. If you think about it, data imputation, it's looking at every single missing value, looking at the structure, looking at the distribution of it, looking at other fields, looking at those distribution of it, matching the correlations, and then coming up with a guess based on certain central tendency. That's a lot of computing. Within my system alone, right here, what we can see, I'll just give you a quick demo here. So this is going to be a challenge since we're all kind of looking at the same screen here. So I'm just going to fire up H2O right here, bring in the enhanced data. So it's going to fire up, initiate H2O. Good thing we're going to comment it out the shutdown because that would be bad. Right here, we're dealing with 4 cluster nodes, 4.4 gigs of memory. So we're going to give this baby a spin. We're going to go down here to data imputation. So we're going to load in our enhanced data, and we're going to loop through every column, and we're going to impute those values that are lined up missing. This would have taken my computer probably about, 3 to 4 hours. So I'm running the imputation right here. So this is the H2O going on right here. It's looping through each of these iterations. So every 78 features, you have high dimensional data. It's going to loop through this, and it's going to give me an error. So that's not so good. I did preload this, but we'll go back up here. We'll do it the right way, Mr. R here.
Is that cluster running locally on your laptop then?
It is. Oh, all of this, that's the beauty of the H2O. It's all localized memory optimization. It's all in-memory optimization. Now, you can run this on a Hadoop cluster, Spark cluster, and things like that, but it's optimizing based off the number of nodes. So let's go back down to our data imputation. And it is now imputing. So right here, this is the funky looking line. You're like, what the heck is that? I've never seen that in R. That's H2O. There it is. It just ran. 78 features, 20,000 rows. Did it in probably less than 30 seconds. Not bad. So now you can see the value of using H2O in that respect. Parallelized processing with data imputation, highly computationally intense, allows for faster data processing. Now the key thing, anytime you do data imputation, you want to go back and look at your data structure. If you've altered the distribution of the original data set, that's bad. Your data imputation data should not have altered the central tendency, the variance, and the distribution of the data at all. So clearly here, when we look at total cholesterol, these are people that do not have diabetes. These are the people that do have diabetes. This is our imputed data. Slightly less right here, but overall the same structure. These are, box and whiskers, if you're not familiar with those. You're looking at your quartiles, your central tendency, which is your median, your values between your first point or your minimal value, your outliers here, your extreme values here. It's just grouped by each of the, whether you were diagnosed with diabetes or not. If you look at weight, same thing. Imputed data, non-imputed data. I see no real shift. Now, if I would have seen over here on the imputed side, this thing go like that, and this one's like this, then we got a problem. Because the data imputations did not function correctly. We've altered the distribution of the data, and we've introduced bias.
Yeah.
So then the weight here is, you can see between the non-imputed data and the imputed data the same, but clearly from an analytical standpoint, you're obviously curious, because here you can see average weight is obviously much higher for those that are diagnosed with diabetes. Yes, sir.
Well, okay, so things like weight or cholesterol, I can see this point, but you were saying specifically people don't answer questions they don't like smoking women who smoke while pregnant won't answer that question. How do you deal with that with this imputational procedure?
Well, it's going to look at the it's going to look at the other fields, and it's going to ascertain a profile. What does a smoker look like? And it's going to impute the values based off other fields, regardless of whether the answer is there or not.
Are there parameters you enter to tweak that?
You can. You can enter in what's called the by clause, and so you can say, I want to impute values by these values here. You can directly impute by, and you can also change whether you want to use mode, median, or the mean. You can choose your central tendency, and when you're using median, you can select the different categorizations of how you're going to do the tiebreaker. Okay, so the next, just kind of wrapping up the exploratory data analysis piece, is once we have identified the diabetes cases and we're looking at the variables here, we want to be able to understand the extreme values between each of the variables between diabetes and not. So this is an index. One is the average. The blue lines are the ones that do have diabetes. The green is those that do not have diabetes. So right here you can say from total cholesterol level here, those that have, well, it's kind of hard for me to see right here, but you kind of get the idea. In fact, let's just open it up in R, might be easier. And I'm using Plotly. I don't know, have any of you guys ever used Plotly? I'm in love with Plotly. It's D3 technology, all wrapped up in R, so you don't have to actually know D3 to use D3. You can just write R stuff. It's kind of cool. So right here, you're looking at, so right here we see an extreme value here. So basically this says those that have diabetes are 70%, or their days of physical health being bad, are 70% higher than the average, those that are diagnosed with diabetes. We can look at, where is age? Age is right here. So those with diabetes, diagnosed with diabetes, are 28% higher than average in the average data set. So this helps us put in perspective the proportionality difference between those with diabetes versus those without. So it helps us identify the extremes. Okay, so now that we've kind of beaten the EDA to death here, what did we learn? You know, just very simple. Weight is higher. Number of sex partners is higher. Number of pregnancies is higher for the positive factors of diabetes. Number of physical days that are is 70% higher, which we saw earlier than the average. And the negative correlations. First of all, this does not mean go out and get wasted back there. You're not going to get diabetes again. Sell the disclaimer, people. So you see the testosterone with negative 14%. Now the interesting thing there, so what would make that interesting based off the other evidence that we've seen here? What would make that interesting? If testosterone's high, the number of babies are high, pregnancies are high, this is low. We're talking about gestational diabetes, right? We're seeing more of those cases, right? So that's kind of what we're seeing.
I have a dumb answer to that. Diabetics meet each other and marry each other.
Yeah, that's very true too. All right, so now we're going into the clustering. So bear with me if you've already, you're master pro at clustering, but those that are not sophisticated in clustering, clustering is just a methodology to be able to group homogeneous data points together through mathematical operations, some sort of distance metric. Could be Euclidean distance, Manhattan, whatever it may be. And there's a myriad of different clustering methodologies. We're not going to review those here. But we are going to review how H2O handles the clustering capabilities. And we're going to cluster these in-Haynes data sets. And we're going to overlay the diabetic cases on top of those clusters. So the clustering algorithms are known as an unsupervised model, meaning that we don't pass it any parameters, we don't train it, we don't learn it. We just give it, we run it, and we have to select a K, which is always the guessing game of what K should be. But K is going to be the number of clusters. So we are going to run that algorithm, but first and foremost, we're going to determine what is K. Now, if you've ever run this on a large data set with 78 features, you know that this is going to wear your computer out. We're definitely talking about 100 clusters here. So running this algorithm on my local PC alone with that many features, that many dimensions, would take about, before I go to bed, I would hit run. I'd wake up in the morning and hope it's done. Probably not. It's still going to be running. With H2O, it only took 13 minutes to be able to iterate through that many dimensions, 78 dimensions, and 20,000 rows, to be able to find the number of clusters needed. Now, if you're curious about how do you know what the cluster is, there's no really hard, fast rule, but the rule of thumb is that as the number of clusters increase and your mean squared error reduces to a point where it's not exponentially dropping, so your diminishing returns, you're still getting value at increasing clusters, but you're not really seeing the exponential value of it. This elbow here is where you would like to see your K be. So here you can clearly see that right here is about 40. Now you can make the argument that, yeah, you could go right here, but you also have to put on your business hat and say from a practitioner standpoint, say that I'm a marketing firm, and you're telling me I've got to send direct mailer campaigns, customized direct mailer campaigns for 100 different clusters. Would it be cheaper for me to make 40? Yeah, probably. Would I get the same thing for the buck? Probably. So you got to kind of put your practitioner hat on there. Will you help me do that? Okay, so while Merle's doing that piece here, yeah, just all right, so we've determined our number of K, and again, H2O process here is very powerful. So it iterated through that many dimensions to determine where the elbow is for the reduction of the mean squared error. See if that did that actually advance? Nope. It's not. That's okay. So, yeah.
So what did you actually run to get the? So this is not the clustering part. You just figured out what is K, what is the
It
value?
is clustering. You're looping through
You're actually
different
running it
iterations
once
of
it-
K
Okay.
using the H2O
Okay.
clustering,
Okay.
or
There was something-
H2O K-means.
Okay.
We're using K-means. I forgot to mention that.
So
We're
just
using
basically goes
K-means.
1, 2, 3, 4, 5, and then.
We're starting at 2
Okay.
because 1
Okay.
points. All right, so the next slide is actually just going to show. Are you good? Put it back in the presentation. We're not covering that either. I didn't have a disclaimer for that. We're not covering that either. Okay, so so the cluster sizes. So now that we have cluster sizes for each of these, you can kind of look at this and say, wow, this is all over the board. We have 40 clusters. Some of them have many observations. Some of them have very few. What we want to be able to determine, and again, this is kind of a business, you got, as a practitioner, you got to understand what your business case is. You could you need a strategy, again, we're going to use that word, you need an analytical strategy. What are you going to do with the leftover clusters that really are not adding value, they don't have a whole lot of observations? In this particular case, we want to keep them, because if we scale, because right now we're talking about 20,000 cases of clinical data. What if that was 200 million, right? So you want to be able to scale that, and if these cluster sizes increase, you still want to capture that population and understand what's unique, because obviously K-means. Missing values. This is kind of a pop quiz to kind of show you, one, you can impute data, but also H2O can handle NA values. Now it handles it different than imputing them. We will see in decision tree and some of the random forest type steps. How does H2O handle missing values? But it does handle it. The good thing is that we see the same story from the imputed data versus the K-means clustering algorithm in H2O. From a multi-dimensional scaling, so we've taken all 78 features and scaled them down. Diseases. That's the point. So then when we overlay the diabetic cases here, we see the proportion of diabetes across each of these clusters. And so clearly here you see high degrees of diabetes in certain clusters and lower levels of diabetes proportions within other clusters. So this is going to help us identify, especially when we do sampling or when we run through our models, of which ones are more likely. If you fall within that group and it already has a high prevalence of diabetes, what is your chances or odds of contracting diabetes if you don't already do? Now the thing about this is that we are not going to do feature extraction through the clustering, even though you could go in and see, look at the features and look how the K-means algorithm scored each of the features and look at each of those scaled values to be able to come up with each of those differences. We're not going to do that. We're actually going to let H2O predictive algorithms tell us which features actually contribute by cluster, which features help us predict diabetes for that specific cluster. Because that's what we care about. We care about which clusters are more prone to diabetes and what are the features that contribute to that. That's what we care about. So what we're going to do here is we're going to take each of these clusters, we're going to run gradient boosting machine, distributed random forest, general linear model, and deep learning, all using our target variable of diabetes, and we're going to do variable importance from each of those, and also we're going to be talking about the loss metrics of getting diabetes correct, answering yes. That's very important. So a quick background, I know that you guys all got a pamphlet on the deep learning aspect, and deep learning's got, probably thousands of parameters that you can go through. It's got neural networks, it's got all kinds of great stuff. We obviously use this for a binary binomial distribution search of the target variable. And so I'm not going to kind of go into detail of each of these, but what I wanted to do is just hit on the key highlights of each of these. In the technical paper, that's what the technical paper's for. It goes through and outlines each of these individually and it allows you to be able to play around with the code and put some more description around that. And there's a lot of great resources on the H2O website to be able to do that. But distributed random forest, if you're not familiar with random forest, it's a tree-based methodology. Each tree gets a vote. So the vast number of trees, you can have multiple level trees. It kind of goes down and say, okay, if your cholesterol is greater than this, then, or if it's less than this, then branch off here and da 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 da. Goes all the way down and gives a probability of our target variable of diabetes, and each node gets a vote. And it's unlike the Iowa caucus, it actually does a split vote. Gradient boosting machine is not like that. Gradient boosting machine combines two processes, even though it is a tree-based method with the boosting gradient, the gradient method and the bootstrapping the boosting machine. You actually are penalized as the number of trees increase. So if you throw 1,000 trees at it and you don't really understand that, the reason is that not every tree gets a vote. It's going to boost every tree, continue to make trees until it finds an optimal solution. That's bad because you can get overfitting occurring. That's why H2O has installed what's called a grind search. And so it helps you look through multiple parameters to help you identify the optimal level of parameter settings that you need for the gradient boosting. Other than that, gradient boosting machines are a fantastic tool. And H2O has done a fantastic job on running parallelized processes that are super quick. So I highly recommend checking that out. General linear model, this is your traditional classical trained linear regression models. And in this case, we're using binomial distribution, so it gets equivalent to logistic regression. But run in a distributed fashion on localized optimization tools. And deep learning, obviously, you guys all got the input there, so that's what that's about. So before we kind of go into that slide there, let's look at one chart here. So what we're looking for is a couple things. So I'm only going to show you one example here. I'm not going to show you all four. In the technical paper, it runs through all four and gives you the features here. But this is distributed random forest. And what this is doing here, all 40 clusters are here. They're all color-coded. And what it's doing is it's looking at which one was identified as feature importance based on some sort of threshold. And it's not really, hard and fast rule, but the most important features were included in each of the clusters. Clearly, the number of clusters here for age makes it a high candidate that a lot of clusters are, considering age as an important factor. Probably age in general is an important factor. And we saw that with the distribution of our box and whiskers chart. We can conclude that as well. The other aspects here that may not be intuitive is pulse rates and other height and different things like that. And the use of Plotly is actually kind of cool too, because you can actually go in and highlight some of these areas. So let's say that we just wanted to highlight certain of these features here, and we wanted to kind of zoom in on them. And we can hover over these. So the alcohol per your systolic blood pressure, the average systolic blood pressure, your height, your pulse rate, poverty level, all those things we can kind of hone in and find out which clusters are some of these clusters actually found those as important features. But the other issue with that is it doesn't really tell me the error rate. And what I mean by error rate, which I'll explain in just a minute. That's not what I want in there. There's also not what I want. What we want to be able to find is a happy medium between the features, the importance, and the error rate. Now this error rate is getting the yeses wrong. And I'll explain that in just a moment in the next slide. So just kind of bear with me. Obviously error rate is bad. You want that to be as low as possible. Here, I'm showing in three-dimensional space the number of clusters. So for example, cluster 26 had blood pressure, systolic blood pressure as an important feature. It has this contribution to the important feature metrics, and it has this particular error rate, 15%. So that's kind of how you read this. And as you kind of go up, the higher the error rate. So that's important, because even though that some of these may be classified as important, but the predictability around each of these, because of the erratic sampling of some of the that the algorithms produce, created higher levels of error rate. And this is where we talk about class imbalance.
Is this also public?
This is plotted. Yes. So let's go in. What do we mean? What do we do about this? Class imbalance. This is a typical case of class imbalance. Class imbalance problems in a traditional when you have balance problems, when you look at your confusion metrics or confusion table, it classifies the no's correctly, and it classifies the yeses usually proportionally correct if you have a good model. For class imbalance, where you have one case that is extremely high and another case that's extremely low, class imbalance will usually predict accurately for the class that's higher in value or observations, but it will be more poor to the ones that are less. We obviously saw 14% of our cases are diabetic, and the 85% are non-diabetic. So within H2O, we're able to identify there's a parameter called balance, class balance. Should H2O balance the classes? And so when you set that parameter to true, it'll do the loss metrics and weight and resample those based off of putting more focus on the yes versus the no. And think about that from a business standpoint or from a clinical standpoint. If you walked into the doctor's office today and I checked your readings today and you did not have diabetes, but I diagnosed you with diabetes, so you go out the door, you change your lifestyle, you come up back there and later to come find out you didn't have diabetes. But let's take the other case. The other case, you come in and you do have diabetes, but I classify you as you don't have diabetes. That's this one here. You go out there, you party like it's 1999, and you come back, and the next day you're in the ER. Which one's more severe? Obviously that one. That's the one so in the loss matrix, when we do the class imbalance, we're giving up the accuracy of the no's, foregoing that accuracy to get more accuracy on the yes. Does that make sense? That's what's most important.
When you're using Flatly or other R packages, are you referencing H2O data frames or R data frames?
That's a great question. These are being referenced from R data frames. Yes.
So can you reference H2O data frames?
Unfortunately, not within Plotly. Now, there's other tools you can, like ggplot2 and other types of charts, but in Plotly, no. Okay, in conclusion, so the last thing is, hey, we've looked at proportion, we were able to cluster these out, we've iterated through all four models, we've been able to look at the features that are most important. What's my risk, Doc? I'll fall into this, what's my chances? What are my chances, right? It's like, tell me the facts, right? Nothing but the facts. If you fall within cluster 5, your chances of getting diabetes across each of these models ranges from 20% almost to 40% depending on the model. If you're in cluster, let's say, 29, your chances are low. And we can look at each of these clusters, and we've run all four algorithms, the gradient boosting machine, distributed random forest, general linear models, and the deep learning. And we were able to identify the scoring or the probability of contracting diabetes. So in conclusion, what we were able to do here is first we opened up the floor, did how to use R, how to use H2O to solve this diabetic problem, which we kind of did. We walked through the enhanced data. We looked at some EDA, quick and dirty analysis. We performed some clustering analytics, and we determined the number of clusters using iterative processing, using H2O clustering k-means that adds tremendous value to the computationally intense process of identifying that. And we performed predictive analytics in all four models to do two things. One, we did predictive modeling on all clusters to identify the variable importance and looking at the error rate for each. And then second, we ran all four models on the entire data set for each cluster to identify what are the probabilities of getting the target variable of the chronic disease diabetes. So with that, I'll open it up to questions, but thank you, and let me know if you have any questions. Yeah.
Which model, did one model generally outperform the others?
Yeah, that's a great question. So the gradient boosting machine typically did better than the others because I actually in the background did the grind search and optimized the parameters. It's difficult to do that with. You actually can use the grind search for other ones, but I just did it for the gradient boosting machine and it optimized the parameters and came up with better results.
When it computes the Euclidean distance, how did
Euclidean
it?
distance.
Yeah, how did it treat the character?
The categorical data?
Categorical.
Yeah, so that's a great question. So for the k-means, we only computed on the numerical values. Yeah. Now for the 4 models, it can handle categorical data. Right. And through these models, each of these models, so the distributed random forest, you can run non-imputed data, so the ones that had the prevalence of the missing values. Now, what it will do, though, is, for example, in a tree node standpoint, when it encounters an NA, it's going to build an entire different tree for the NAs. And then it's going to branch up into those NAs. So that's different than data imputation because it is somewhat changing the distribution of the data, if you think about it. But it does treat it, and you come up with very similar results if you start playing around with it. So I'd encourage you to kind of play around with the non-imputed data, with the imputed data, and sort of test those algorithms.
What about the like low end K groups? Like sort of you created estimates for some groups that had like what 5.
Right.
I mean, how did it just, to me doesn't seem like those
Actually,
estimates would be very strong.
in fact, well, that's a great question. So let's go back to where was it? Here.
Yeah, like those
So
4.
check out cluster 5.
Yeah.
Very small. Now check this out. Cases of diabetes, very high. They feel like almost all of it.
Yeah.
And I don't have it here, but in the 3D chart, it had the best predictor of diabetes than all the other clusters. So even though it was low in size, the prevalence of diabetes in that particular, it flushed out all those features that are contributing to the diabetes. And so that's why the k-means cluster is categorized it on its own. Because remember, k-means, diabetes is a categorical field. It didn't know. It had no idea cluster 5 was so prevalent of diabetes. But then when you run the algorithms on that cluster, it's saying, what's up with that? You know, all these features, it has a high target rate for diabetes.
But you run the algorithm specifically on each cluster separately,
To
right?
get the features, but
Okay.
you run it to get the probability for each of the clusters, you run it on the whole thing.
Okay. Cool.
Can you show the code that was used to create the Plotly chart?
Which one?
Like the 3D one?
The 3D one? Yeah. You guys like Plotly? Still checking if I can find my mouse. Okay, so for example, so a 3D plot here. We're going right here, we're imputing data, we're doing some EDA here. These are more charts. Now in the technical paper, it's gonna have all this. So later we're gonna give you the link, you can download this, you can do every bit of everything I just showed you in the technical paper. So when you're doing something like this, you kind of watch those in alignments. So, but for the 3D plot, it's gonna be down here where we're doing our modeling. Supervise. Oh, I did forget to. I think this goes without saying with this group, but the 4 models that I ran, the gradient boosting machine, the distributed random forest, and general linear models, and the deep learning are all supervised learning. We're training, and we're doing a holdout, and we're doing testing. And that kind of goes without saying there. Yeah. So for the distributed random forest one. The Plotly code for the 3D plot is okay. So it's a filter here, you're looking at the percentages and it's a scatter 3D. Make sense? Yes, sir.
So when you do the supervised learning on each cluster, did you use the whole data to train or you did cross-validation?
No, you train the sample for each cluster for the feature importance or for the probability of the risk of getting diabetes per cluster. Because those are two different questions. If you're looking for variable importance for each cluster that did contribute to the diabetes target variable, then it's iterating through all 40 and sampling each 40. But if you're talking about the general population of the risk for each cluster of diabetes, then it's training and sampling on the whole thing. Make sense?
In the standard R, when I have categorical.
I'm sorry.
In the standard R, when I have categorical variables and I want to cluster, I use PAM.
Yeah, so that would
Can I use
that
this
would
on
turn
it?
them into continuous variables. Where you can
Yeah,
discrete.
could I use it in under H2O the way you use
Yeah,
it?
you can use those as long if you want to undiscretize your data
Oh.
and do it that way you can. Yeah.
Did you use an ensemble model?
Yeah, by definition, the gradient boosting machine and the deep learning are doing ensemble languages, and they are doing the ensemble in the background as you iterate through those.
But I mean, of all the models.
Of all the models, too. But that's a nice next step. So you could read the technical paper and form an ensemble.
And what were the performance of all the models? As far
Accuracy or speed?
No, speed, yeah.
So the gradient boosting machine again performed the fastest and the most accurate, just because the parameters were optimized. But all of them generally, through the iteration of each 40 clusters took about 2 minutes for the whole data set, or not 2 minutes, like 40 seconds, but for the whole data set for each model took about a minute maybe. And we're talking like 1,000 trees, and things like that. So, not bad. I think he had a question next.
I was just going to ask what your experience been with munging within H2O. Have you had any experience, maybe not in this data set, but
Not a whole lot.
Do you notice any difference in performance for each one of the algorithms, for each one of the clusters? Like, did you get different results?
I didn't really test that. Are you talking about the speed?
You said
Or
that
the
you use
accuracy?
all the algorithms for each one of the clusters, right? A
Yeah.
different model.
Are you talking about speed or accuracy?
Accuracy.
Accuracy, yeah. So gradient boosting machine.
For all the clusters?
That's a good question. I didn't check each one, but for the ones that kind of spot checked a little bit,
Like
gradient boosting machine
or,
typically do better.
So, this is an H2O question. Can you use H2O to, increase speed of reading data in? So if you have some huge data set,
Right.
it's given as just a data set instead of using a read or a free or something like that.
Right,
If you
so-
run through H2O, does that improve the performance of it?
I don't think that's an H2O problem. That depends on your network problem. So if you're pulling data, let's say directly from a web page into your session of R into H2O, that's going to depend on the speed at which you're.
Suppose I have a huge.
But if you have it on your local,
Yeah.
and you're uploading it there, then yeah, it can improve. It can improve some of their processing as well.
You said this stuff is repeatable and you can try it?
Yeah, there's a technical paper on the website, so if you have any questions, I think we're going to send out the information. So both the technical paper, this presentation, and some more information about the Colaberry Data Science Center of Excellence is all going to be published there. So you can download it for free and try it on your own.
Is the R code available?
Yes, the R code is in there. Merlin will publish it out to the meetup, however he does that.
was the paper published?
It was published on the website.
Conferences or journals?
No.
I will push the link right away into the meetup group as well as all the media channels like that.
Okay. All right, thanks everyone. Thank you.
Thank you very much, Josh. If you stay for a few more minutes, we're almost just a few more minutes. If you like the presentation and if you learned something today, I would like you to see if you can contribute to the group as well. If you're already working on H2O right now, share your experiences on what is working for you, what is not working for you. Or if you're just exploring it, even share your experience on what you find, because this is not your day one on data science. If you are coming to H2O, you're already coming from different tool or framework. So that comparing and contrasting always helps people to learn it. So please share your experiences. We are looking for anybody to come and contribute to the group. If you're interested to either speak or share some information, just ping me on the Meetup group, and we will schedule another Meetup group as well. And many of you are asking about the training program itself. I will push those links as well as more information there. And I would like to bring upon our Chicago team that will be available here in the 1831 building if you have any questions or if you need any help with your H2O or in particular data science itself. If you need any help, they will be available.
I'll you too. Alright, so I'm Serena, I'm the marketing manager here, and I'm here to assist. I want to again thank you all for coming, and also please, if you have any questions, you want to hang out, eat some more, take some food home, please feel free to do that. And we're here to answer any questions that you may have, so if you guys want to stand up and like kind of talk to all of us or any of us and say, hey, I have these questions, how do I do this, how do I do that? We're here to help you guys. So our motto is to help you guys through everything that you guys may want to get through in our programs, because you know that we have a little bit more of an invested interest in you. We want you to be successful. So please stick around if you have any questions. We're here to help in any way. Ali, you have anything to say?
Well, she stole my whole food thing. My name is Ali. I'm the Chief Automation Officer at Colaberry. I appreciate you guys coming out. You know, like she said, feel free to reach out if you have any questions or anything. Also, you got food in the back. Please take it with you. Lorenzo?
All right, Lorenzo Rodriguez. I was kind of sitting outside meeting with everybody, taking down names. You guys probably hate me at this point, but I just want to introduce myself as the Business Intelligence Architect with Colaberry, and the site manager for the Chicago Colaberry. So if you guys have any questions, then we'll be here at the 1871 building. But other than that, thank you guys for coming out, and hopefully more to come in the future.
And for any of you that are currently exploring H2O or you need any help with data science, we actually have a framework which will help you discover what you need, what kind of framework you need, what kind of strategies that you could use, and we could help you with the discovery process for free. So feel free to just ping us if you need anything. We actually have lots of collective experience as a team, and we want to learn from you, and we want to contribute as well. So feel free to respond to Meetup group or just send me an email if you are interested to either share your experiences or share whatever you are learning, or if you need some help. Thank you very much. Great evening and drive safe.
You want to say something?